Hello everyone, welcome to Physics online classes for class 12 students. Let us continue chapter 6 Electromagnetic Induction. Today we are going to solve Ncert numerical problems part 1. As we have completed the theoretical part of electromagnetic induction, we studied in this chapter about Faraday and Henry experiments, Faraday's law of electromagnetic induction, magnetic flux, Lenz's law. Lenz's law is the consequence of law of conservation of energy, motional EMF, energy consideration in motional EMF, then relation between induced charge and changing magnetic flux, eddy currents and their applications and disadvantages. After that we studied self-induction, mutual induction. Then at last we studied AC generator. So this completes theoretical part of electromagnetic induction. Let us solve Ncert numerical problems. The first problem, predict the direction of induced current in the situations described by the following figures 6.18a to 6.18f. You can observe these diagrams one by one we can observe here, and let us find the direction of induced current in the situations described by the following figures. See here, the direction of induced current in the closed loop or in the circuit is given by Lenz's law. This point you should remember. The direction of induced current in a closed circuit is given by which law? Lenz's law. So here the given pairs of figures. For example, in the first figure, magnet and the coil. In the second figure, there are two coils. Between the two coils, they kept a magnet. So and so on. So between the pairs of the figures show the direction of induced current when north pole of the magnet is moving towards or away from the closed loop respectively. If that magnet is moving towards or away from the coil, how the direction of induced EMF takes place in the closed loop, that we can find. Yes, using Lenz's law, the direction of induced current in the given situations. So that I am going to predict here. First you can observe the diagram. We considered a bar magnet and the coil. You can observe here. This is south pole of the magnet. Now here you can observe the direction. The direction is towards the coil. When the south pole of the magnet is towards the coil, magnetic flux linked with the coil changes. Induced EMF takes place and hence the current is produced in the coil. But in which direction? Whether it is anti-clockwise or clockwise, that you have to remember. See here, when the north pole of the magnet is moving towards the coil, then the current is moving in anti-clockwise direction. When the north pole of the magnet is moving away from the coil, then the current is produced in clockwise direction. But here they had given south pole of the magnet is moving towards the coil. So that indicates south pole of the coil is moving towards the coil. It means the induced EMF takes place in anti-clockwise direction. When south pole of the magnet, it is moving towards the coil. So now the current is moving in anti-clockwise direction, that is from Q, R, P, again Q. So in which direction the induced current takes place? It is along Q, R, P, Q. Right? Then come to the second diagram. They kept a magnet between the two coils. Now here you can observe again. The south pole of the magnet is moving towards the first coil. It is moving towards the first coil means again it is moving in anti-clockwise direction, that is from P, R, Q, P. Right? So it is moving towards anti-clockwise, that is along P, R, Q, P. But now here you can observe in the second coil. North pole, it is moving away from the second coil. Observe here, this is moving away. If it is moving away from the second coil, so here the induced current takes place in exactly opposite, that is clockwise direction, X, Y, Z, X. Here it is along X, Y, Z, X. Right? Then come to the third diagram. Here they had given two coils along the common axis. The first coil is connected to a tap key. Here there is a tap key, and also it is connected to battery. The first coil is connected to battery and the tap key. So we are going to induce a current in the second coil. But in which direction? Here the sentence is given, tap key is just closed. When we press the tap key, current go on increases, magnetic flux also increases. Because of changing magnetic flux, induced EMF takes place. So the current is produced in the coil. But in which direction the current is produced? The current is produced in anti-clockwise direction because the current is increasing. That is YZXY. YZXY. Because the current is increasing, flux also increases, so that the current is produced in anti-clockwise direction. If that tap key is released, if the tap key is open, then the induced current takes place in clockwise direction. Right. Then come to the fourth diagram. Here they had given again the two coils which are fixed along the common axis. We are going to induce current in the first coil. The second coil is connected to battery and this is a rheostat. It is connected to battery and the rheostat. When the battery current changes, flux also changes, the current is produced in the first coil. Here the sentence is given, rheostat setting being changed. When the rheostat changes, current in the second coil also go on changes. Here they had given the direction. You can observe here the current is moving in this direction. Right? So because of changing rheostat, current changes, flux also changes. So the induced EMF takes place in the first coil. But in which direction the induced EMF takes place? So here the induced EMF direction is from, you can observe, this is in the clockwise direction. Because here when rheostat is setting be changed means current decreases, flux changes, induced EMF takes place, so that it is moving in clockwise direction, that is from Z, Y, X, Z. Then come to the fifth diagram. Here there are two coils. The first coil is connected to battery and the tapping key. Second coil is connected to, you can take this is a resistor. We are going to induce EMF in the second coil. Here the sentence is given, tapping key is just released. When the tapping key is just released, then in which direction the current is flowing? We know that when the tap key is released, current decreases, flux also decreases, induced EMF takes place in the second coil, and this current is moving in clockwise direction. So we can take X, R, Y, X. In which direction? X, R, Y, X. Observe the last picture. Here this is a conductor. Magnetic field lines are lying in the plane which are having the closed loop. Here the sentence is given, current I decreasing at the steady rate. Steady means constant. At the constant rate, if the current is changing, then flux also changing at the steady rate. That indicates no current is induced in this conductor. So, no current is induced. So, this is all about the direction of induced currents in the given pair of circuits. Yes, the second question. Use Lenz's law to determine the direction of induced current in the situations described by the figure 6.19. The first figure, a wire of irregular shape turning into a circular shape. The second one, a circular loop being deformed into a narrow straight wire. Yes, now let us study about the first diagram. You can observe a irregular shape that is turning into a circular shape. As the loop changes from irregular to circular shape, if it is changing from irregular shape to circular shape, then its area increases. When area increases, the magnetic flux linked with it also increases. So we know according to Lenz's law, the induced current that should produce magnetic flux in the opposite direction of original flux. If the original flux is in clockwise, then induced flux is produced in anti-clockwise. For this induced current that should flow in the anti-clockwise direction. It means the direction of current will be along A, D, C, B, A. In which direction the current is flowing? It is flowing along A, D, C, B, A. It is in anti-clockwise direction because we know according to Lenz's law, induced current should produce magnetic flux in the opposite direction of the original flux. Come to the second diagram. Here, a circular loop being deformed into narrow straight wire. As the circular loop is being deformed into a narrow straight wire, then its area decreases. When area decreases, the magnetic field linked with it also decreases. So when magnetic flux decreases by Lenz's law, we know that induced current should produce a magnetic flux in the direction of original flux. So for this, the induced current should flow in the anti-clockwise direction. It means the induced current should flow in the anti-clockwise direction. It means the direction of current will be along. You can observe here, it is flowing along anti-clockwise direction, that is A dash, D dash, C dash and B dash. It is deformed into a long narrow straight wire. So in this direction the current is flowing. Yes, next question. A long solenoid with 15 turns per centimeter has a small loop of area 2 centimeter square and it is placed inside the solenoid normal to its axis. If the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 seconds, what is the induced EMF in the loop while the current is changing? So we have to find induced EMF in the loop when the current is changing from 2 ampere to 4 ampere. Now first you can note down the givens here. Number of turns of the solenoid is given. Number of turns of solenoid. It is given how much? 15 turns per centimeter. Or you can convert in terms of meter. For 1 centimeter there are 15 turns. For 1 meter means multiplied by 100. So we will get 1500 turns per meter. Then this is total number of turns of the solenoid. Now I want number of turns per unit length. Number of turns per unit length. Total number of turns is denoted by N. Small n gives number of turns per unit length means 1500 per unit length means divided by 1. So we will get 1500 turns. This is for number of turns per unit length. Then here the solenoid has a small loop of area. Area is given A equal to 2 centimeter square, or you can convert in terms of meter square, that is 2 into 10 raised to minus 4 meter square. Then current carried by solenoid. Current carried by solenoid changes from, it is given 2 ampere to 4 ampere, it is changing. Therefore, change in current in the solenoid. Change in current. Change in current in the solenoid. So generally we can write it as DI. So DI equal to, we can write 4 minus 2 final current minus initial current. We will get 2 ampere. This is change in the current. Similarly, this changing current takes place in the time 0.1 second. So change in time we can write dt. It is given 0.1 second. What is the induced EMF in the loop while the current is changing? We have to find induced EMF. So we know that according to Faraday's law. What is the equation of Faraday's law? That is E equal to d pi divided by dt. Let us take it as equation 1, where pi is induced flux through this small loop. So in place of pi, we know that pi equal to B dot A magnetic field lines passing through the given surface. And also we know the value of B, magnetic field, B equal to mu naught Ni. So we can write in place of B as mu naught Ni, mu naught Nia. This is the value of pi. Therefore, E equal to, substitute in equation number 1, d by dt of mu naught Nia. Or we can write this equation as mu naught Na keep as it is. These all are constant. Remaining is d by dt of I. Right? Or you can write mu naught is absolute permeability and its value is 4 pi into 10 raised to minus 7. Number of turns is 1500. Number of turns per unit length. Area is given, that is 2 into 10 raised to minus 4 into di by dt, that is 2 ampere, divided by time is 0.1 second. After calculating, we will get the final answer 7.54 into 10 raised to minus 6 volt. This is the induced EMF in a given solenoid when current changes.